So let's remember, every bloke and his dog's having a go at this. Television was that thing. This was the new magic. This was what was going to let people in their own homes see right now what was happening in London, what was happening in Paris or New York or anywhere. You could see all around the world in your own lounge room. Didn't have to go to the movie theatre when the films finally came out. You'd have it at home. So, Vladimir Zworykin, working in St. Petersburg, worked with Boris Rosing, working on television. You may have heard people say, oh, the Russians invented television. Well, look, they were one of any number of people. Remember that thing about the inventors? Everybody knows about it, everybody's having a go, everybody's doing stuff. Some of it works pretty well, some of it doesn't. But people tend to say, oh, my nation are the leading scientific beings in the world, therefore we invented everything. Well, no, sorry, you didn't. They were leading developers, and Rosing and Zworykin's work led through to what would become the first practical camera tube. But right back then, it was demonstration only. Meanwhile, a guy called Kalman Tahanyi threw open the doors. He went back and read the Maxwell equations, which they make my head spin, but he could obviously handle them. He discovered something. He worked out that if you continue to deposit electrons on a site, you'll get a build-up of charge. I'm waiting for a pause for someone to say, can they really do it? Of course you can do it, come on. We're so familiar with the concept of charge, of electrons and stuff, electron physics, we're so familiar with that it's really hard to imagine that it took until Tahanyi's patent that someone worked out you could actually accumulate charge in a vacuum on a photo surface. But it was Tahanyi's patent that showed that was practical. And he proved electronic scanning would be the future because he described an all-electronic system. He correctly described the limitations of disk scanning, low image brightness. He described a camera tube that would do this. Big photocathode illuminated by your lovely faces. Creates a charge on that large photocathode. The scanning beam comes on and picks off that intensity, that one, that one, that one, that one, and sends them back to zero, right? But in the meanwhile, following where the scanning beam's been, the charge is building up again. So essentially, that beam is picking the full intensity of every individual site on the photocathode, unlike the mechanical one, which is going pick, 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 and only getting instantaneous values. Now, there's a guy called Farnsworth. He was a farm boy, amazingly. Grew up on a farm, was interested in stuff, and put together an idea for a camera tube. It was called the image dissector. It was completely passive. There were no cathode, no electronics. It's almost like a solid-state vacuum device. Down this end, we've got the photocathode, light's coming in, and I get an image on the photocathode. That entire image is now sent down the tube in its original form. It's pretty snappy. He's got this cloud of electrons, or this plane of electrons, just moving them down and preserving their exact shape and disposition. Down at the other end, they hit onto a collecting electrode, which sounds like it's just going to give a bright spot. What he did do then was he put a couple of deflection coils along and waved it across, or down the length of the tube, and increased it so that he finally had a scanned image going across the photodetector. It couldn't accumulate charge though, so we're back to exactly the same problem mechanical scanning have, that you're only getting instantaneous values. You're not able to build up charge in between. You'll read in the references that it had very low sensitivity and can only be used in furnaces. Well, I'm not convinced about that. The references I've read talk about it competing with other electronic systems for outside photography or outside televising. There are some hints that it was possible to use it in studios with high illumination. I've not been able to find anything definite about that, but I think there may be another reason, and that is the three big letters RCA. Because David Sarnoff at RCA is very well known for being very entrepreneurial and, well, he liked to hoover stuff up. I'll probably mention it later, but I'll mention it now in case I don't. He's quoted as saying the Farnsworth patents cost us $50 million to overcome. That's $1930. So Sarnoff was behind Zworykin to do an RCA camera tube. How much there was skullduggery and stuff, I don't know. But I suspect that the low sensitivity of the Farnsworth image detector is not the whole story. So let's have a look at it. It's a pretty amazing stuff. I'm going to talk quite a bit about emission, secondary emission and stuff. Reading back, it's surprising just how complex all the electron physics were with this. This one's fairly simple. We've got a photocathode. It produces negative electrons, so it's got to be a cathode. Yep, that's good. And there's a number of charged electron accelerator rings around the outside. So as the charges come off the cathode, they're progressively pulled forwards down the tube. And finally, they end up down at the end of the tube and we get a signal coming out. Now you'll notice I've got a gadget called a photomultiplier, and that is a device that will give a, what's the voltage gain of 1,000 like? Is that pretty good? Please someone say yes. Thanks, Pete. Voltage gain of 1,000 is pretty good. How about 1,000,000? That's even better. Photomultipliers can achieve current gains or voltage gains in the tens and hundreds of thousands and the odd few million. So wherever you see someone using a photomultiplier, it's a pretty good clue that their original design was pretty rubbish and they had to put in the noiseless amplification of secondary emission. Here we go. 4, 8, yeah, that's right. 16, whoa! I had 1 electron in, I got 16 out. Gotta love that. So that's a fairly low performing photomultiplier because I'm only getting a gain of 2 times for each stage or each dynode. Still, if I go 10 stages, I'll get a gain of, I go 10 stages, I'll get a gain of 1,000. If I go 11 stages, I'll get a gain of 2,000. If I get 12 stages, I'll get a gain of 4,000 and so on. If I've got a multiplication factor of 4 per dynode, I only need 5 dynodes to get a gain of 1,000. It's quite practical with a multi-dynode design and high secondary ratio to get very, very, very large gains. Here we go. I'm going to send the Mariner space probe to Mars in the 1960s. I need to get on a 8 or 10 months journey, 350, 400 million kilometres, and I need to get to Mars within orbiting range. Okay, how am I going to navigate? Well, I can't use initial conditions. I don't know when the rocket took off and its motor finally did its final burn, I don't know exactly where it was in space. Got an idea, but what, to the nearest metre? No. I don't know its final velocity to the nearest kilometre per minute or second, or I don't know. And I don't know its exact angle of aim. It's impossible to take the initial conditions and navigate all the way to Mars. I can't use inertial navigation. They did that in Apollo, didn't they? They used inertial navigation to fly to the moon, but the very last bit was flown by the 2 pilots. And I don't have a pilot on board my Mariner spacecraft. So I have no means of using initial conditions or anything to get to Mars. So let's go back to an age-old system called celestial navigation. What I'm going to do is I'm going to put a camera on Mariner. I'm going to aim it up at the star Canopus. Now I've plotted out the flight path, right? I guess I have. I know exactly what angle of view and what rotation the spacecraft should be relative to Canopus every foot of the journey, if I want to calculate that exactly. So what I need now is a photosensor that's sensitive enough to pick up the light from the star Canopus and actually steer the spacecraft on its way to Mars. And they used a photomultiplier. The original NASA papers are, well, I like reading stuff like that. The initial NASA papers say they could get a gain of 10 to the 8 just inside the tube itself. So they could get a gain of 100 million with no cathode, no heater, nothing, always on if you need it. But they decided they weren't going to be greedy because that was pushing it a bit, and they knew that they had a gain of 10 to the 7, 10 million, available reliably. But they said, oh, look, let's not be greedy. We'll just dial it down just to a gain of 1 million. That was about the last scientific application of the image detector, but it reminds us this whole idea of secondary emission is a very powerful but probably now almost forgotten technology for getting gain inside an electron tube with no noise. The noise figure they quoted was about 50 picoamps of current, which is nothing. But that was the end of that technology. So let's go back to Zworykin. He had designed a camera tube. It was unique. We haven't seen another one like it. I'll do the diagram in a moment, but the electron beam came from behind the photocathode. So there's the front of the tube, there's the photocathode beams coming from behind. But it was based on a thin aluminium film to support all the clever stuff. No problem, I'm just going to aim the electron beam at the aluminium sheet and go straight through. Should work. What it did do was stored charge successively. That image on the photocathode would be picked off progressively, but after it had been picked off, it would start accumulating again. And it's a unique design that could not be made to work. Bam! Hate that. That was his 1923 patent, and it's fascinating. I, again, did a bit of reading to find out why it wouldn't work. There's his original patent drawing, and the bit inside the red circle is what we're interested in, particularly that 34, 35, 36 assembly. So we've got the scanning beam coming in from your right, got the scene illumination coming in from your left, and they meet up in this centre mechanism. Well, how should it have worked? Well, this is how it should have worked. We've got the electron beam coming in, it hits the aluminium sheet, there's a layer of aluminium oxide, insulator, pretty good insulator that, and then deposited over the lighting side, there's globules of potassium hydride, which is a photo emitter. So that's easy. All you do, bring the electron beam in, hit the charged area, that pushes off electrons from the charged area, and the electrons go forward. There's a positively charged mesh, and they go onto the mesh. It doesn't matter if they disperse, because they're only coming from one place. So it should have worked. However, it didn't. Although it was able to get something out the other end, it was very low sensitivity, it was very, very poor resolution. So something must have been happening, because he's intended quite a sharp beam hitting just one photo site. What I think happened, and it's again been difficult to find out exactly what, but I reckon it was something more like this. The beam would come along, it's an electron beam, it would hit the metallic surface of the aluminium, and you get a sort of spattering effect. If you can imagine getting an almost hard piece of pottery clay and just hitting it at a wall, it's going to spatter. So I think there are two problems. I think that there would have been impact dispersal up and down, and I think also that there would have been lateral conductivity or lateral current flow in the aluminium. Aluminium is a pretty good conductor, so I think that although he'd done everything right, he hadn't anticipated that his very fine electron beam would get dispersed on hitting the backside of the target. And just to pay a bit of respect to young Vlad, that whole thing was 12 micrometers thick. So even back in the 1930s, they were able to create and manufacture stuff like this. The problem was, it was a bit like mechanical scanning. There was a fundamental flaw in the design that could not be overcome. I'm just going to pause there for a moment and look at what's happened. There's been competition between those two inventors. The image dissector has been pushed out of contention. This is a 1923 patent. There was a patent issued to Farnsworth which overrode the 1923 Zworykin patent. By this time, Zworykin was working with RCA, and David Sarnoff was not going to let anybody else dominate the world of camera tubes. RCA went back to the patent office and said, no, you cannot uphold Farnsworth because Zworykin's 1923 is the primary patent. And the office said, but you've used the words will produce an electron image in your 1923 patent. We have examined your patent. We've discovered that your device does not produce an electron image, but we've discovered the Farnsworth device does produce an electron image. So the Farnsworth patent was reinstated, or was upheld, and is the foundation patent for vacuum tube camera tubes. So Zworykin went back and he revised it. So he came up with the electronoscope. Unique design, it's the first widely used camera tube. It was in use for at least 20 years. It used electron beam scanning from the front, right from the image side, not the back. Okay, he gave up on that. Stores charge between scans. So we've got over that problem of the picking off the instantaneous values. We're going to get stored charge. We pick off that one, but where we've been, the charge is building up again. It was capacitively coupled, which I'll talk about again in a moment, so there was no true black level. You had no idea what amount of current or signal level was black, so that was a problem for particularly the receiver. You would see a very washed out picture, or you'd see one crushed down into the black because there was no definite black level. And again, as we'll see, because the electron beam comes up from underneath, you'd expect a nice rectangular scan, yeah? What you get is a keystone or trapezoidal scan because the top of the target is a different distance from the bottom, a bit annoying. And as well as that, he expected that he would use a secondary emission effect, which he sort of did, but it wasn't very tidy. Let's have a look at it though. There's a perspective view. We've got Felix, thanks Felix, back again. Lens is projected onto the photocathode. Underneath that, well, you couldn't put it in front, so it's got to go underneath. You've got the electron gun, which is aiming up at the photocathode. There's one over in that CRV-59. That's a flying bomb camera. That camera was designed for one mission. You'd go out in your B-29 with one of these tagging along beside you. When you got within, I don't know, 10 miles of the target, the bomb aimer would turn on his television, turn on the camera on the pilotless aircraft with about a 1-ton payload, or 1-ton explosive payload, and he would fly into the target relying on the television signal being relayed back from the flying bomb. So that's actually a camera with an iconoscope in it. Have a look a bit later. So, second generation, there's a side view, and maybe it makes sense. We've got the photocathode up there, got an electron gun, need one of them, a collector ring and an output connector. So, the electron beam's coming up the tube, it's been bent a bit because it's been deflected, and when it hits the target, what Zworykin was relying on was the high velocity electrons would hit the target and would cause secondary electrons to spill off from each site according to how much charge was there already. So if you had a 1 electron and a 4 times amplifier in the secondary emission, one in you get 4 out, 100 in you get 400 out, and so forth. So that was his idea. It worked, it could be made to work, and that was the first practical camera tube. The problems it had was, like I said, it had no true black level, it had the keystone scanning, and there was a problem with the secondary electrons. He expected they would all be snapped up by the collector ring. That was the aim, but it's like throwing talcum powder on a floor. It's not always going to land neatly, and he had a problem with poor performance there. It's capacitively coupled, which is unusual, but the mica plate completely insulates the metal back plate, so you can't determine what zero light input is, because there's no actual DC component where you can work out where your zero is. However, it worked. And if you see a TV camera with that long foot on it from historical photos, it's a good chance it's an iconoscope, because remember the iconoscope had the scanning section down at an angle below the optical axis. Electronic scanning timeline. I'm going to go back to Willoughby Smith because his discovery of the photoconductive effect was critical to all this stuff. Look, everyone's had a go, haven't they? I'm going to go to the final development. We had 1941, the United States had 525 line broadcasting. That was put into abeyance during World War II, but it recovered as their 525 line system. The USSR had a go. With 625 lines. Europe established the 625, and France went to 819 lines, a very high resolution system for their black and white TV. So that's effectively the time span, and that's about when my primary reference, which is Abramson, ends, and that's about when electronic television proved that it was a completely practical, it was a home entertainment quality medium. It could be beamed across the world fairly soon on. By about 1960s, we'd be recording it. I'm going to call the end of development the iconoscope. I now want to see where we got to. I'm not going to do these in detail, but the first one was the image orthicon. Zworykin and RCA recognised the difficulties with the iconoscope, so they came up with the orthicon. Remember this thing about secondary emission. When I have electrons incoming onto a sensitive surface, secondary emission means if I put 100 in, I get 400 out. So this is a completely noise-free way of amplifying weak signals within the tube itself. I don't have to go to an external amplifier with bandwidth problems and stuff. It all happens inside the tube. Secondary emission, it's the reason we invented the pentode, to get away from that troublesome effect in tetrodes. It's used as a noiseless method of amplification, and it's critical to a number of different sorts of tubes. So, Zworykin had wanted to design an orthicon, ortho, on the same line as image. He cheated a bit because he snitched the image transfer principle from the Farnsworth image dissector. It had much higher sensitivity and it had an inbuilt electron multiplier, and that took over from the iconoscope and was the next phase for about 20 to 30 years. In case you're wondering what one looks like, here's one I bought earlier. That is a 4-inch I/O. Pretty big, isn't it? I wouldn't use it as a weapon because they're kind of precious, but that was the standard camera tubes from the sort of 1950s to about 1970s. If you wanted a 3-tube colour camera, would that be bigger? Yeah, it would be a lot bigger. So it was very large, worked well enough, but it was very power hungry and was just not practical for anything portable. But here's our I/O. So there's the image section, Farnsworth image transfer, so the photocathode, and we transfer that onto a target, which is a microscopically thin piece of slightly conductive glass. I think it's about 15 micrometers. It was very, very thin. Behind that, we had this really weird and wonderful idea. So you've got your scanning electron beam which comes down and interacts with the photocathode. That makes sense, yeah? Now your problem is how are you going to get that electron signal back down the tube? Well, that's not a problem. You very carefully do all the scanning and acceleration and alignment and stuff so that when an electron hits the target, if there's a charge there, it liberates other electrons which are captured and then go back down the tube the opposite way to the photomultiplier. I hope that makes your head spin, because it does mine. The fact that it's got a photomultiplier tells me that Zworykin's original design, the orthicon, didn't have enough sensitivity. They had to pull in the photomultiplier to get the extra amplification without noise inside the tube itself. And unfortunately, this one, the end is blanked, but inside that would be those multiple diode construction that you use for an image multiplier. Big, expensive, not portable, not really going to work that well. But there's a photo of one. Then someone went back and said, oh, really, why don't we just get photocathode, an electron gun, aim the electrons down, hit the photocathode, get the signal. So they went all the way back to Willoughby Smith's idea of photoconductivity and said, I know, front of the tube we'll put a metal plate, well, a really thin one so the light can get through, then we'll put the photocathode. We're going to make it conductive. So where the scene is bright, there's low resistance across that barrier. Where the illumination's low, there's high resistance. That means as our electron beam comes down and goes across, in the bright areas with low resistance, a lot of electron current will come through. Or in the dim areas with high electrical resistance, we won't get much current coming through. Why didn't they do it that way in the first place? Really, I mean, how simple is that? You've got a glass tube, you've got a target collection ring, you've got a photoconductive target, a couple of coils and stuff, and that's it. That was the final stage of development in electron camera tubes. It's the Vidicon. There's a number of varieties. There's a Satacon, Chalnicon, and so forth. They're all using that same basic mechanical structure. So if I talk about a Vidicon tube, I mean a Vidicon tube. And I did bring one in. Oh yeah, there it is. Here's one I took out of a camera earlier. In fact, I've misled you there. Here's 3, because this is a colour tube. Now, it might look like it's only a single sensing device. This one's from Sony, who I have a bit of admiration for. They're pretty clever. On the front of that, which is not visible unless under a microscope, there's a very microscopic colour filter. So colour comes into here. There's a bit of clever stuff done inside the tube. Now at the other end, you get a colour picture. So starting with the iconoscope as the first practical camera tube, 20-year lifespan, it's got to be pretty good. We went all the way through the complexity of the image orthicon, came to the elegant simplicity of the Vidicon, and finally using Vidicon construction technology and so forth, we wound up with this little fella. I hope you can see it on camera. Maybe I should hold it up there. There we go. They look like that. And there's the Vidicon family. You may have heard of the Plumbicon, which was a Philips proprietary. It's a bit different chemically, but it's still essentially the same Vidicon construction. And the family, from the iconoscope, first one we had, through to the image orthicon, there's 2 different sizes there down to Vidicon. So it's all history. I mean, all that stuff's from way back. Well, Baird tried to build a recording system for his mechanical scanning. Shouldn't be too difficult, should it? He managed to do it. He publicly abandoned it because it wasn't going to work well enough. But some of the phonovisions were donated or given away, and they were preserved for the future just by being sort of thrown off the end of the shelf. And there's a sequence of actual images. The one that you saw before was Stookie on the NHK unit. I'd actually image stitched together to make a continuous movie. Notable figures? Okay, Nipkow. He made the foundation payment. His disk scanning system is what everybody said, yeah, we can do something with that. The world's first public TV station, Fernsound sender, Paul Nipkow. Campbell Swinton was a leading theorist of the day, and he kept saying, it's got to be electronic, it's got to be electronic, whatever you do, mechanical scanning is not going to be practical. And he was, although not an inventor as such, he was a principal theorist in saying, no, we've got to go electronic, it's the only way to do it. Boris Rosing, who did a mirror drum scanner, in St. Petersburg, and he was a mentor to Zworykin. So although we can't say that Rosing was a primary inventor, he certainly set the scene for the success that Zworykin later had. Tanya said, no, we can't do this mechanical stuff. I've shown, using the Maxwell equations, that we can do charge accumulation. And it was charge accumulation that was pivotal to the success of electronic scanning. Farnsworth, farm boy invents first television camera. Yep, that's pretty much exactly what happened. Fascinating history. Zworykin, early work with Rosing, and it was Zworykin's persistence that finally got to the iconoscope. We'll just quietly pass by the fact that Sarnoff tried to resurrect the 1923 patent, which was never going to work. And in England, a guy called Isaac Schoenberg developed a tube very much like the iconoscope, but it worked better. It was called the CPS emitron. Prehistory, and you've got a handout for this. Has anyone got any ideas? Well, yeah, look at them. But that's early on, up until about 1920, and then in 1920, oh my God, okay, everybody's having a go, did I say? Everybody. Mechanical TV, you can put it together in your workshop, in your kitchen, whatever. So everybody led to this enormous explosion of investigation. Regrettably, all of that work helped pave the way, but didn't result in practical applications, and it was always going to be electronic. Right back in 1931, a guy called Manfred von Ardenne demonstrated all electronic television, got images, and once you'd got images, that was like someone inventing photography. Look, I took a photo outside my window, look, that's what it looks like. Once someone had done that, then everybody was going to have a go. And I'm going to say that electronic television matured, as far as we're concerned, in 1949 with the 819 line French system. References, you've got them. The best single reference is a book by Abramson. He said that I'm only going to accept references where I know that there is a patent awarded, that there are signed, witnessed laboratory notes, that there are eyewitness accounts of a demonstration signed as depositions. He said, anything else? Look, I'm sorry, I'm not going to take that seriously. The book itself, I think it's about 320 pages. It's got 57 pages of reference, so you can see this guy's really done his homework. And I think he mentions 320 odd people. There's a bit of detail in the book review in coming radio waves. I've run out of words. Thank you. Just quickly, any questions? Yeah. And Andre, mate. Okay, so Andre's talking about tube burn. If you expose the tube to really bright light, and you could do it just accidentally. Like if I've got a burn-prone tube, I've got the camera, I've got lens open, I go like that. How many lights are there? 1, 2, 3. When I cap it off, or when I look at a white page, I can see 3 bright trails across the picture. Even looking at a piece of white paper, it's never going to get any better, probably. It's called image burn. The Vidicon with its selenium target was especially sensitive. Yeah, oh, you've got 3 of them. Okay. Man, you just burnt 3 tubes. Have you got your job application ready for another radio station, TV station? So,
tubes cost $2,000.
yeah.
This is a little backstory. We were out at a race course doing the horse races one night. We thought we were putting the lens in the camera, and the person in the truck left the exposure open because we lifted the camera up and pointed straight into the bright lights that were lighting up. But burned all the tubes at $6,000 worth of damage in the money.
Yep.
And we had to go for the rest of the night and try and just sort of look through the burn marks of the tube.
Yeah.
But I to this day never knew which part inside the tube got the burn.
It was the actual the photosensitive target was damaged by the excessive light. So that was one of the reasons, so it was a problem with Vidicons. That was one of the reasons they went to different target formulations. There was a Satacon, Chelnicon and a couple of others. They were more resistant to burn, but every camera operator was instructed not to let that happen. It could happen as accidentally as what Andre said. You just tilted up and went past a bright light, and that permanently wrecked the tube. Charlie?
You're not supposed to hold Vidicon tubes upside down either, because little particles can drop off the cathode and blow through the mesh.
Yes, absolutely. Inverting if there was anything left in the tube, where was it going to end up? It was going to end up on the target, and it was probably going to stay there. And again, it's Andre's thing about having to retube. Yeah. Right.
Have you heard of a problem with cameras called lag? Where you focus on a bright light, say it's a candle, over a candle, and it moves slightly, it follows the image and there's a flat.
Yes, yes, it's called lag. The aim is that as the scanning beam goes across the electron image on the target, it completely discharges, or if it's a resistive system, it completely goes open circuit. That's not guaranteed to happen, and it's what we call image lag. So what you're seeing is the time it takes the image to be discharged, even when the actual incident illumination is no longer in that particular place. Yeah. So the Vidicon suffered from two really particular problems. Firstly, it was very sensitive to image burn, as Andres told us. Second, it was very sensitive to image lag. What was nice about it was, depending on the voltage you put across the photocathode, its sensitivity would change. So if you wanted to reduce the sensitivity, you go outside in the sun, everything's just blown out completely, not a problem. We'll just increase the bias on the tube itself, and that pulls its sensitivity down, and you've got a correctly exposed picture. That wasn't possible with the later formulations, but the Vidicon, the original selenium target, was, I'll just call it so fragile, that there was a lot of impetus to come up with a more robust chemistry. I think there's still a couple of handouts over there. That camera over there, I might have said it's actually from the United States Army Air Force flying bomb. So that one is unusual because it's got an iconoscope tube in it. It's probably one of the very few iconoscope cameras anywhere in the world that's still sort of working. So hey, it's a bit special.
Most of them blew up in a building, didn't they?
They did. What's unusual about it, just the final thing, is every camera I've owned, from antique Kodak cameras to box brands to blah, 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 video cameras, you name it, camera, the lens has some kind of aperture control. You go outside, it's too bright, dial down the aperture. Even my old box brand has got an inside-outside switch. That one is the only camera of any kind that has no control over the incoming light. What's that tell me? It's not very sensitive. And I'm done.
And thank you, Ian.